All right, so let's talk about PA1. So this is available on Canvas, but we'll do this up here too. Uh-oh, projector is shutting down. All right, we'll be back in 84 seconds. So programming assignment 1, so you're implementing a linked list. Okay, using this array type structure that we've been talking about. So you're going to define a struct node just like ODP 202. You're going to make an array of 100 struct nodes. That's going to be the memory from which you create your list. You're going to use -1 to represent end of list, but I want you to use a #define to create a symbol called myNull and set that equal to -1. Okay, that's really important. It's going to make life easier on PA2. You could just use a -1, but make a symbol called myNull, define it to be -1, and anytime you want to use that -1 for the end of the list, use the symbol myNull. Okay, and you'll see why in PA2. And you're going to do two things. One, you're going to write a set of functions for creating and examining and manipulating a linked list. So you're going to make the init function, you're going to make something to insert, to search, delete, to print, and so on and so forth. And then two, you're going to make a main program that lets the user interact with a linked list. And it'll take a series of one-line commands that allow the user to say, insert this number, delete this number, search for that number, print out the contents of the list, and so on. Okay, the main program is basically for testing the functions that you're developing to work with a linked list. So let's talk about the main program first, because the main program is kind of a 224 exercise. It's stuff that you did in some of your programming assignments 224. It's stuff that doesn't involve data structures. It doesn't involve all of this linked listy kind of stuff. Your main program basically prints out a greater than sign. Okay, that's the prompt for the user to type something in. And it waits for the user to type commands. And the user will type something, hit enter, and then your main program calls the right functions to do whatever the user is requesting. And it's a very, very minimal language of things that the user can ask. So you can type the letter I, lowercase, space, followed by an integer, and that should insert that number into the list. So if I say I space 5, it should do all the stuff we're doing on the pictures when we insert a 5 into the linked list. And it should do this in a way that the list stays sorted. We're only going to allow a number to be in the list once. So if I say insert 5 and 5 is already in the list, you should print a message saying node already in list. Otherwise, if you succeed, just print out the word success. Now, I'm grading this myself. It's not going through an automatic assessment. So if you make this lowercase instead of uppercase or something, it's fine. But I'd like you to try to stick to this as much as possible, and in particular, avoid inserting a node and printing out 5 lines of information that were useful for debugging, okay, but potentially confusing to a user. That's me. So, one line message if you succeed or if the node's already in the list. All right, the command P says print out the nodes in the list in order, one per line, or on one line, with the numbers separated by spaces. So if you've inserted a 2 and a 5 and an 11 and you say P, you should print out 2, 5, 11. S is followed by a space and an integer, and it's searching for a number, and it should print out either found or not found, depending on whether the number is in the list. D is used to delete a number from the list. And if you succeed in deleting that, print out success. If I'm deleting a number that's not part of the list, say node not found. And then X exits the program. Anything else is an error and should print out a short help message basically showing each of these commands. You can make it one line per command or something. Just to remind the person, oh yeah, I use X to exit, or I use D to delete, if you can't remember that. And after each command, it does whatever it's supposed to do, and then it prints out another greater than sign. That's a prompt, and it waits for the user to type in another command. All right, I'd like you to do reasonable error checking. So what's reasonable? If I say I and I hit enter, that's an error because I didn't put a number after it. If I say I space hello, that's an error because I didn't put a number after it. Okay, if I say I space and I put in a number, take that as valid. And I put a note down here, if you say something like I space legal integer space something else, don't worry about the something else. Just take that as insert 25. Or if the person types in some big, long, ridiculous number that scanf converts to some different value, that's okay. Okay, you only need to be as diligent as scanf makes it easy to do. But if you just say I, or you say I followed by something that's not a number, print out an error message and keep going. Okay, definitely don't segfault. That's the worst response. Same thing with searching for and deleting numbers. If it's not a number that's applied, or if no argument is given after that, print an error message. All right, and then deliverables, basically take all of your code, make sure it's commented well, and there should be a lot of comments in your code. That's not a requirement, it's a sort of statement of reality. Right? This code is going to be fairly complex. Every function should definitely have comments on a lot of the lines of code, possibly every line of code. If you say, you know, array bracket x dot valid equals 0, why are you doing that? It's really clear to you when you're writing that statement, because you're at the point where you're trying to delete a node, you're trying to free up that location in the array. But to somebody else, or to you when you come back to it 2 days later, it's not going to be as clear. Just throw a comment there, // set the valid bit to 0 to indicate this node has been deleted. Right? It will make your life easier. All right, comment the beginning of each function. Right? If you're making a function called search for data, put a comment block in the beginning. What are the parameters? If you're passing 3 arguments to it, what are those 3 arguments doing? Make them reasonable names too. Don't make them ABC. Call it linked list array, initial node, numbers looking for, or something, right? But put some comments in there. Describe what they do. What does the function do? What are the possible error conditions? What does the function return, if anything? Right? So start thinking about these kinds of things if you were going to hand this off to someone in exchange for $500 million, right? And you're really hoping that they like your code enough to give you all that money, right? You'd want them to be able to look at this and know what the code is doing, right? Know that something's happening in here. So what would you put in there? Comment block in the beginning of your main program with the name, class, date, assignment number, etc., all that usual stuff. And a make file. Okay, so you definitely want to put this into separate files. You could do 2 files. You could have a main program, and you could have, functions.c with all of your linked list stuff. Or every function could go into its own file, if you like. You can split it up however you like, but it's going to be easier the more you partition it. So make a make file. And then bundle all that up into a tar file and upload it to Canvas. When I'm grading, I'm going to download all of the submissions. I'm going to have a bunch of tar files. I'm going to take the first tar file. I'm going to say tar xvf, name of the tar file, dump everything into my directory, and I'm going to say make. and then I'm going to say whatever the name of the program is, and I'm going to test it. Okay, if that doesn't work, if I say make and it says no such file, make file, or it gives me compile errors or something like that, you're looking at least a 25% deduction, because I'm going to write back to you and say, hey, your make file doesn't work, and you're going to have to turn it in late. So make sure that you go through these same steps yourself right after you've uploaded. Download it, push it over to an empty directory on the Linux server, do the tar xvf, say make, say whatever the name of your program is, and run your test cases. All right, the way you do this, the order in which you go about this can make a big difference as to what the experience is. So the print routine is really useful and fairly straightforward to code among these other routines. Right? You just started the first node, the sentinel. You see what it points to, print the data. If that points to something other than my null, go to that location, print the data, and keep going. And once you have a print routine, your life gets a lot easier developing these other things. Because you try to insert something, you want to know if it worked or not, call your print routine. As long as you know your print routine works, you can use that to help debug the other functions. If you make your search routine first, you don't have to worry about these details of what if I try to insert a node that's already in the list. Before you do anything else, call your search routine. It returns a number, 1 or 0, telling you whether it's in the list. If it's in the list, print your error message and return. You're done. If it returns a 0 saying it's not in the list, you don't have to worry about that case where it's in the list. You know that it's not, and so you can just go ahead and do your insert routine. Same with delete and so on. All right, so let's talk about the details of the linked list code. So the init routine, you're already writing. Okay, it initializes the linked list to be the argument LL to be an empty linked list. So the node at index 0 should point to my null, indicating there's no other nodes in the list, and the valid flag in all other nodes should be cleared. So that's your ODP. But your ODP is also setting particular values. For example, it's setting the next field on all the other nodes to minus 99999. Why? Because if you accidentally use one of those and try to index your array with negative 100,000, it's going to segfault. And it'll tell you right away there's something going on. And it'll give you a line number where that happened. So it'll help you with debugging. All right, there's an add function. So add takes a struct node array, and it takes a number. And the goal is march through your data, find the right place to insert, and once you found it, go ahead and sandwich it in between those two nodes. And it returns a simple flag. If it succeeds, it returns a 1. If it doesn't succeed, it returns a 0. The main reason you won't succeed in this add function is if you run out of space. So you're searching for a new location in the array to use, and all the valid flags are set. You can't insert. So your add is going to come back and say 0, I didn't succeed. All right, print just takes your struct node array and prints out the data that it finds in the linked list. So the nodes are stored in sorted order, and so it's automatically going to be a sorted list when it comes out. And if you make this print everything on one line with spaces in between, your print command is just a call to your print function. It's really one line of code at that point. All right, delete takes a linked list array and a number and tries to delete it from the list. And if it succeeds, it returns a 1. If it doesn't, it returns a 0. Search takes a linked list and a number, and it searches for it, returns a 1. If it finds it, returns a 0 if it's not. Those are the main functions that your main program is going to interact with. But these functions themselves need some other functions to make them work. For example, we're often going to be going through our array looking for an entry where the valid flag is 0. So make yourself a function called getNode. And getNode should take a linked list array and start marching through from the beginning until it finds an entry where the valid flag is 0. And if it finds such an entry, it should set the valid flag to 1. So it takes care of that last piece that I keep forgetting, which is to set the valid bit to 1. And then return the index of that new node. If it goes through the whole array and it can't find a place where the valid flag is 0, return myNull. And you gotta use this function every time that you need to find a place to store something in the array. I'm going to insist that you do it by calling getNode. Functionally, you could take the code you're putting in getNode and just put that inside your add routine, but you'll lose points for that. Okay, so I'm forcing you to modularize a few aspects of this. One of those is getNode. The other is releaseNode. So if you want to delete a node, it's stored at this location, right? Remember, the last thing you do is you take this thing's valid field and you set it to 0. Make a function to do that. So releaseNode just takes a node array and an index and sets that index entry's valid flag to 0. It's another one-line function, but I'm going to insist that when you delete a node, you call releaseNode to make that change.
I thought you said that if you pass an struct and you change something inside of it, it doesn't change the struct in the main.
True, but we're passing pointers to structs.
Oh.
Right, so this is an array. So it's like passing an array of integers to a function. If that function changes x bracket 5 up here will also change. But if you just pass an integer and you change it in the function, it doesn't change in the caller. All right, still making sense? So this is 4 pages, but it's 3.5 pages, but it's worth reading it and thinking about it and highlighting it and things like that. There's a lot of detail in here, but it's all important detail. Okay, and some of it's really important for PA1, some of it's important for PA2. All right, let's talk about abstract data types. So this is a general notion, and it's a notion that will dominate a lot of what we do in 223, where we're in object-oriented programming. But it applies here also. So here's the idea. We have this main program. And the main program is getting commands from the user, and it's making calls to this linked list code. This collection of functions that you're writing, init, insert, delete, search, or whatever I call them, add, delete, search. Your main program should not have to know anything about how these linked list functions work. It should understand the high-level behavior. When I call the add function, it will insert a new number into the linked list and keep the list in sorted order. That's all the main program knows about the add function, and it returns a number. It tells me if it succeeded or not. That's it. The main program should never be looking at valid bits. It should never be looking at anything .next. It should never be looking at anything bracket some index. That's not part of a linked list. A linked list is a way to initialize, a way to add, a way to delete, a way to search, a way to print. For us, that's it. So the idea is there's this interface between the main program, or the calling code, and this linked list code. The linked list code is going to come into some lower level code, and this is where we're doing, you know, data bracket I dot next equals blah blah blah. But up here in the main programming, we're just saying add, delete, print, and so on. This is the most important thing about working with data structures, is this clean division between what functionally these things are doing and how they're actually doing it. For example, we're setting myNull equal to -1 while we're defining it, right? If we suddenly change myNull to be -15, this code's going to change. This code's not. And this code's absolutely not. If we decide we're going to start with the 99th element in our array, when we look for a valid flag equal to 0, we're going to start from the bottom and work our way up. So our first node gets stored in location 99, the next in 98, the next in 97. That's going to change some of this code. It's probably not going to change this code, but it should absolutely never ever change any of this code. Because this notion of adding a node by storing it in the next location in the array where the valid flag is 0, that's not part of how main looks at a linked list. That's the implementation of a linked list. Okay, so this is something to keep in mind as you're writing your main program and trying to split things between, here's my main thing that's doing input and parsing, here's my linked list code, here's a code that gets a free node or releases a node, right? We like these clean interfaces. And if you do this right, when you get to PA2, that's not going to change. The main program is going to look exactly the same. Because it's just calling add and delete and print and search. And your linked list code is going to change very, very slightly. And this lower level code we're going to throw away. And we're going to use what the operating system provides for us, which is malloc and free. So if you stick to this clean division of labor, this clean view of main sees a linked list as this stuff, this thing does linked list operations, but when it wants to find a free node, it calls this routine and so on, then PA2 becomes, you can almost write a regular expression to convert PA1 to PA2. In fact, I had one student who actually did that. I don't think he used a regex, but he did a global replacement in the editor and got PA2 out of it. So the work you're doing for PA1 is down in the trenches, get your hands dirty, okay, but it's also going to work for PA2. And then when we get to PA2, we can concentrate with the language of pointers and what things are pointing to and so on and so forth, and not have to worry about also trying to figure out a linked list because we already have done them once in PA1. So keep that in mind, this separation between layers. This goes under the name of information hiding, by the way. So the fact that myNull is equal to -1, that fact is hidden from the main program. In Java, we would actually use the keyword private, which would mean that outside callers couldn't actually see this variable, right? So this works well with object-oriented environments. All right, questions? That's likely going to take some time before questions start to occur. But like I say, use the discussion area on Canvas and or send emails because we don't get to meet as a class for a week.
what you've all described there, basically having interfaces between your levels of code is more or less the idea behind portability, isn't it?
Yeah, totally. Because if you wanted to run this on a different system, as long as that system implements those low-level routines, you just recompile your main program and you're good to go. And somebody comes up with a better, faster way to store your nodes in an array, if you're tinkering with the array in your main program might break now. If you're only accessing the array through the routines that were provided to you to interface with it, you recompile and you're good to go. And for the array thing, it's not going to be 100% as clean as I'm describing, because the array is kind of a wonky way to do this. But the idea is to be as pure as possible. Well, the next thing I was planning to do is start talking about pointers and stuff. After telling you don't have to worry about them. But change of gears here. Don't forget everything we've just been talking about. But let's talk about pointers and stuff. Well, let's talk about GDB. Speaking of pointers, has anybody looked at the GDB quiz? All right, look at the GDB quiz, and then we'll talk about GDB. We've done enough last quarter in 224 to be able to do that quiz, but if you haven't been doing that stuff or practicing it, it may be rusty or confusing. So take a look at the quiz when you get a chance. Try it if you can, and if questions come up, ask them.
Are you going to let us know when we should have knowledge of each quiz?
So for quiz 1, you should be good to go. For the other quizzes, I gotta go back and actually look at them, but my suggestion would be take a quick run through them and keep in the back of your mind what's on there, right? So that as we're talking about things, you can start thinking about, oh, this is related to such and such, right?
So I'm looking at the GDB quiz right now,
Mm-hmm.
and I mean, you can't really look at it without a start.
Yeah, but you can take it as many times as you want. There's no time limit. There's no
So I
penalty
just
for
take
multiple
it and
attempts.
Look at what it wants.
Yeah, yeah. So we say integer x. So that tells the compiler we have a variable named x. It's going to be an integer. We want to store this somewhere in memory. So here's our memory. My memory always starts at 100 because I'm lazy. So there's the first 17 locations. And the compiler and the loader linker collectively decide where to store x in memory. And let's just suppose it decides to store x starting at location 100. Okay, so integers are 4 bytes, so locations 100 through 103 will collectively store the value of x. And since each memory location stores 1 byte, and we've got 4 bytes, we've got to choose how to store those 4 bytes in here. Do we store the least significant bit here or here? So do we run x in this direction or this direction? Well, that has to be decided by the compiler and the architecture of the CPU, and it varies from machine to machine and system to system. But usually we don't have to worry about it. For a while we had to worry about it with networking, because we had computers talking to each other, and if one stored x with the least significant byte here and another stored the most significant byte here, you'd pass one number to a machine and it would interpret it differently. So it can pop up, but for what we do, we don't really need to worry about it. That's called the endianness of the numbers. So x is stored at this location, and let's say integer y, and maybe for whatever reason y is stored down here. And I'm going to say integer star p, so p is a pointer. Well, pointers need 8 bytes to store them on a 64-bit machine. So maybe it's going to store p right here. It wouldn't, but maybe it is. Alright, so I say x equals 0. How does that change the memory of the machine? It's going to put zeros into these 4 locations. And I say y equals 1, and let's just suppose least significant byte goes into the address higher on the page of paper. This is going to set our memory like this. Those are bytes, so there's 8 bits associated with them. So these are all zeros. This is 7 zeros followed by a 1. Alright, now I say p equals address of x. So that ampersand means address of. So what is the address of x? 100. It's the address where x begins to be stored in memory. X could be 4 bytes, could be 400 bytes, but the address of x is the starting memory location for x. So this would store the number 100 into these 8 bytes that we call p. So again, assuming that the least significant byte is stored at the top, this would be 100, 0, 0, 0, 0, 0, 0, 0. So I see some confused looks. So on a 64-bit machine, pointers will be 8 bytes. Yeah. You usually only use 12 of them, but they allocate 6. Sorry, you only use 6 of them usually. 12 nibbles. If you do this on a 32-bit machine, pointers will be 4 bytes. If I try to say y equals p, you can see there's a problem, right? Because p is 8 bytes and y is only 4 bytes. So I'll actually get at least a warning from the compiler when I try to do this. And if it succeeds in doing it, I've got a real mess on my hands now, because it's going to start it right here, and it's going to use these 8 bytes. And now I'm munging p. So we'll comment that out. What if I say y equals star p? So when we say star variable name, we're saying the thing pointed to by that variable. So let me just put some comments here. So ampersand variable is the address of the variable. And star var equals thing pointed to by variable. So if we say y equals star p, the first thing that happens is the CPU looks at the value of p, and it finds this 8-byte number that's equal to 100. Since it's star p, it says what's stored at location 100. It's a 0, 0, 0, 0. So this sets y equal to 0, 0, 0, 0. So it does this.
You go over that again.
Sure. So when we say y equals star p, first thing the CPU wants to know is what's the value of p. Well, it knows that p is stored starting at location 10C, and it knows that p is 8 bytes. So it looks at the 8 bytes stored starting at location 10C, and it finds this 8-byte version of the number 100. Star p says go to the memory location contained in p. If p is 100, go to memory location 100. If p was equal to 200, star p would say go to memory location 200. It's 100, so we go to memory location 100, and we find the number 0. So this is saying set y equal to whatever it finds here, which is 0. So it says set y to 0, so it copies a 0 into the memory stored for y, allocated for y. If you write something crazy like y equals star asterisk x, that's what we just did. We took the address of x and we stored it in p, and then we said y equals the thing pointed to by p. Well, that's exactly what this is going to do. It's going to take the address of x and then take the thing pointed to by that. This is exactly the same thing as just saying y equals x. So this is why when you have a function you make an increment function, and you have some main program which says, you know, integer data equals 5, and you say increment data. Well, everything is passed by value. So when I call a function with a variable name, the CPU finds the value of that variable, which is 5, and it basically says increment 5. So it jumps down here, it starts executing this code by setting the variable x equal to 5. This says set x equal to 6, and then return. It hasn't touched data. So when I come back here, data is still equal to 5. That's the whole notion of passed by value. But if I do increment the address of data, and I tell this is a pointer to an integer, well, the address of data, let's say data is stored at location 104. This is saying increment 104. And down here, if I say star x equals star x plus 1, okay, I come in here, x is set equal to 104. If I look at star x, that's the thing stored in memory location 104, which is a 5. So star x equals memory at location 104, which is equal to the value of data, which is equal to 5. We add 1 to that, we get a 6. This says star x equals 6. Star x means the thing at memory location, whatever x is, 104. This says set memory location 104 to have the value 6. Well, what is at memory location 104? Data. So this basically says data gets the value of 6. So now when I return, data is equal to 6. That's the reason with scanf, when you're trying to use scanf to read the value of an integer, you have to pass an ampersand in front of the variable name. Because if you don't have an ampersand, it's just copying the value that the variable currently has, and it's never going to change. If you pass the address, if you pass a pointer to that variable, the function can use that pointer to know where to change, where to write that new value. So how does this work with arrays? So I'm going to simplify my memory map. And I'm not going to show it byte by byte. I'm going to show it a word at a time. And so let's say integer x bracket 3. So the compiler decides where to store x in memory, and maybe it decides, okay, I'm going to store the first element here at 104, the second element at 108, and the third element at 10C. So if I say x bracket 0 equals 15, x1 equals 25, it copies the 15 into here, it copies the 25 into here. Now if I call some function and I pass it x, and in this function, this is the void function, if we're expecting an array, we declare an integer pointer. Let me give it a different name. Call this data. So it's an integer star data. Well, this function is expecting a pointer. I better be passing a pointer. What value is it actually passing to this when I say fun of x? Say again? Pointer, what's its value? 104. Remember in C, if you have an array named x, if you just say x, it's the address where that array begins. Since x begins at location 104, when I call fun with a value of x as an argument, it passes the address where x begins, 104. So when I get into my function, data is equal to 104. And if I say something like data 2 equals data 0 plus data 1, how do we find the ith element in data? We had this formula on Monday. It's 104 plus 4 times I. Where does it get that 104? It gets it from the value that was passed in. So this will be whatever stored at memory location 104 plus 0, which is right here. This will be whatever was stored at memory location 104 plus 4, which is right here. So this will add the first two elements of x. And this is stored at location 104 plus 8, that's 10C. So this will add the first two elements of x and store it in x bracket 2. So in our function, we're manipulating this argument array, but it's exactly the same array as what we passed in. Okay, that's why we can change pieces of a structure array, even though we're not explicitly passing the address of it, because when we do this, we're actually passing the address where the array begins, so our function can get to the address of each element in the array. All right, so that can be fairly convoluted depending on how many times you've seen this, but it's stuff to keep in mind. Down the road, probably starting Wednesday, we're going to be looking at actually manipulating the memory of the computer. And so we're going to be doing these kinds of things a lot. So if you're not comfortable with pointers, you'll be starting to get more comfortable with it next week. But go back and refresh yourself as much as you can from 224 and from 121. Because it's going to be beneath everything that we do throughout this course. Again, when we're making data structures, we're really talking about how to structure this stuff in memory, how to position it in memory, because what we're heading to is where we're going to have structures that contain other structures. But it's painful to take a big structure and try to shove it inside another structure, especially if this is the same type of structure as this. So we're going to work with pointers to structures. And in the case of a linked list, for example, we're going to have a node, and it's going to have a piece of data, but it's also going to have a pointer to another struct node. Right? But it's going to have to be a pointer, because we can't include a struct node as part of a struct node. It's recursive. If we use pointers, we can get out of that. So we'll be doing that next week. All right, so I'll stop here for now. Emails, discussions come Friday if you've got the time, if you don't have a conflict. And otherwise, I will just see you next time.
I cannot believe